Hi everyone, we're going to go ahead and do another example problem, conservation of momentum, again in two dimensions, and this one's a little bit different because we have two objects in motion initially that are going to come together. So, it says a 1325 kilogram car moving north at 27 meters per second collides with a 2165 kilogram car moving east at 11 meters per second. The two cars stick together to determine their final speed and direction. So I always like to start with a picture, and I have my before and after picture. So my before picture looks like this one car, 1,325 kilograms, moving this way at 27 meters per second. And I have a second car moving this way, 2165, moving this way at 11 meters per second. Okay. Then we have the collision. And so these two cars stick together. Says. So I have 1325 and 2165, and since momentum is conserved, they're going to move off in some direction like that. And we're supposed to figure out how fast and what direction they're going. So what I'm going to do is, since we have two dimensions, I need my positive x and positive y. So just to keep things simple, I'll say that everything's moving in positive x or positive y. So initially, my initial momentum is, and we got to separate things x and y, so my initial momentum in x, so initial momentum in x is equal to 11 times 2165. And the other one's not moving in x at all, so plus 0. My initial momentum in y is equal to 27 times 1325, and again the other one's not moving in the y direction at all, so plus 0. So that tells me my initial momentum in the x direction, 11 times 2165, is 23,815 kilogram meters per second. The initial momentum in the y direction, 27 times 1325, is 35,775 kilogram meters per second. Which means after we collide, that still has to be the case. So now I'm going to come over to my after picture and I'm going to draw in my components. I have 35, whoops, this is y, so sorry, 35,775, and I have 23,815. Now, those are the components, which means I can find the hypotenuse. So my final momentum is equal to the momentum in x that I started with, squared, plus the momentum in y, squared, square root, Pythagorean theorem. So I'm going to take 23,815 squared plus 35,775 squared, square root that, and I get a momentum of 42,977. This is not the answer to the question. This is how much momentum these things have. So I just found this momentum collision, and it wants their final speed and direction. So if I want their velocity, since momentum is mass times velocity, I need to divide off the mass. So 42,977, which mass? Well, they're stuck together, so I have the mass of both of them. So equals 2165 plus 1325 times v. And if I go ahead and divide that by that sum, then I come up with a velocity of, that was wrong, let me try that again, 42,977 divided by 2165 plus 1325 equals 12.3 meters per second. Now, before we go anywhere and move on and find the direction, I want to see if that makes sense. 12.3 meters per second. Okay, this car was initially moving at 11 and this car was initially moving at 27. Okay, this car got a little bit faster, this car got a lot slower. Why did this one have a much bigger change? Well, it's a much smaller car, so it'll change more. So it does actually make sense that I have a velocity of around 12.3 meters per second. Now the last thing to find is the direction, which is this angle right here. You could find a variety of them, but I'm going to use that one. So I'm going to use the arctangent of the two momenta I found. So arctangent of 35,775 divided by 23,815, and make sure your calculator is in degrees for that, and I get an angle of 56.35 degrees. Now that isn't really the direction because we told it in east and north. So if this angle is 56.35 degrees, then it's 56.35 degrees north of east. So 12.3 meters per second at 56.35 degrees north of east. And that tells me the final speed and direction of the car. It's conservation of momentum problem.